What if the most important message ever delivered to humanity was not written in language at all, but in geometry? That is the unsettling question raised by the strange case of 3I Atlas, an interstellar object that entered our solar system and immediately began to challenge ordinary explanations. It did not merely look unusual. It behaved in ways that seemed to pile anomaly upon anomaly. A persistent sunward antitail, a tightly focused jet that remained coherent over astonishing distances, a rotating inner structure that appeared to resolve into three distinct jets, spaced almost exactly 120 degrees apart, chemical signatures that defied expectations, and a trajectory filled with coincidences that some researchers found difficult to dismiss. Most astronomers still regard 3I Atlas as a natural object, most likely an unusually active interstellar comet. That remains the mainstream view, and it is an entirely reasonable one. But the object has inspired intense debate because its details do not fit neatly into ordinary cometary models. The deeper researchers looked, the more the puzzle seemed to grow. This is the story of that puzzle. The images that intensified the controversy arrived quietly at the end of 2025. 17 exposures from the Hubble Space Telescope, taken on November 30, December 12, and December 27, offered the clearest look yet at the behavior of the interstellar visitor. At first glance, the raw frames showed what astronomers expected: a bright central condensation, a fuzzy surrounding coma, and an extended plume of dust and gas. But when the images were processed using techniques designed to highlight subtle asymmetries in cometary comas, something more structured appeared. At larger scales, the dominant feature remained the antitail, the strange extension that seemed to point toward the sun rather than away from it. At smaller scales, closer to the nucleus, the processed images suggested three distinct jets radiating outward with near-perfect symmetry. Each was separated from the others by roughly 120 degrees, dividing the circle into equal thirds. That geometric neatness was what set imaginations on fire. Natural explanations exist. Comets can produce jets when volatile ices beneath their surfaces warm up and sublimate, dragging dust into space. If several active regions happen to be spaced around a rotating nucleus, multiple jets can appear. Under some viewing geometries, those jets can look surprisingly organized. Nothing about that, by itself, requires technology, and yet 3I Atlas seemed to press every explanation to its limit. The antitail was not a faint or ambiguous feature. It was long, narrow, and persistent. In some processed views, it looked like a tightly collimated beam, far more focused than the diffuse outflows normally associated with cometary dust. If that interpretation is correct, the source of the outflow must be very closely aligned with the object's rotation axis. Otherwise, the spin of the nucleus would smear the structure into a broad cone or fan. That observation led to one of the central statistical arguments in the debate. If the main jet was aligned with the rotation axis, and if that axis itself was closely aligned with the direction of the sun, then the geometry required a very specific and seemingly unlikely orientation. Some analyses placed the odds of that alignment at roughly 1 chance in 500. A probability like that does not prove anything on its own. Improbable things happen all the time in astronomy. The universe is large enough to generate remarkable coincidences, but the case for 3I Atlas did not rest on one unlikely feature. It rested on the accumulation of... That was what made the object so provocative. One oddity could be dismissed as chance. Two could still be coincidence. But by the time researchers had assembled a list of unusual properties, some began to wonder whether a simple cometary explanation was being stretched too far. The object's trajectory was unusual. Its orientation was unusual. Its chemistry was unusual. Its persistent sunward behavior was unusual. Its rotational light curve was unusual. The symmetry of its inner jets was unusual. Each anomaly had a possible natural explanation, but no single explanation accounted for all of them at once. The debate became not whether any one feature could be explained, but whether the full package could. To understand why, it helps to begin with the anti-tail itself. Comets are supposed to have tails that point away from the sun. That is not a rule of thumb. It is a consequence of physics. Dust particles are pushed outward by radiation pressure, and ionized gas is driven outward by the solar wind. As a result, the visible tail of a comet normally streams away from the sun no matter which direction the comet is moving. 3I Atlas repeatedly appeared to violate that expectation. From the earliest high-resolution observations in mid-2025, astronomers saw a sunward extension ahead of the nucleus. At first, some argued that it might be a perspective effect. Anti-tails can sometimes appear when dust is confined to a narrow orbital plane and viewed from a particular angle. In those cases, a sunward feature is not truly material streaming toward the sun, but rather a geometric illusion caused by the arrangement of dust in space. But the anti-tail of 3I Atlas refused to vanish. It persisted across multiple epochs, across changing viewing angles, and even after the object had passed perihelion and begun moving outward again. It remained coherent when simple perspective effects should have changed. It stayed narrow when diffuse dust should have spread. It kept pointing sunward despite shifts in the object's trajectory that should have altered the appearance of any fixed structure. This persistence was deeply uncomfortable for standard models. If the antitail were produced by ordinary large dust grains ejected at high speed, then those grains would need enough momentum to travel sunward against solar radiation pressure before being slowed, turned around, and eventually pushed outward. That is not impossible, but it demands unusually high launch speeds and a mechanism capable of directing dust into a focused stream. A weak, random outflow would not do the job. The anti-tail implied something vigorous and organized. That was one part of the puzzle. The inner jets were another. Processed Hubble imagery suggested that near the nucleus, the coma was not simply lopsided or irregular. It contained three apparent jets arranged with near-equal spacing. One feature pointed roughly away from the sun, while the other two extended laterally on either side. Over time, the brightness and exact orientation of those jets changed, consistent with a rotating body. But the underlying geometry appeared to remain intact. If those jets came from surface vents, then the vents themselves would have to be arranged with surprising regularity. That is not impossible. Natural surfaces can contain symmetric patterns, but cometary nuclei are usually the products of chaotic histories: accretion, impacts, outbursts, thermal cracking, fragmentation, and erosion. They are not known for preserving clean geometric organization over immense timescales. A natural comet can absolutely have multiple jets. The question raised by 3I Atlas was why they looked so neatly spaced and why the overall outflow pattern remained so structured. One popular analogy was the lighthouse. Imagine a rotating body with a jet source near one pole. As the object spins, the jet would wobble around the rotation axis, tracing a narrow cone through space. If the wobble was small, the beam would remain concentrated rather than spreading into a broad fan. If the axis were directed toward the sun, the beam would appear to stay sunward even as the object rotated. In that case, the anti-tail might not be a conventional tail at all, but the visible path of a tightly directed outflow aimed almost exactly at our star. That model could account for several observations at once. It explained the persistence of the anti-tail. It explained the narrowness of the structure. It explained the rotation-linked brightness changes. And it explained why the geometry seemed organized rather than chaotic. But it also created a new question. Why would the axis be aligned that way in the first place? Rotation axes of small bodies are normally expected to be random, or at least random enough that a near-perfect solar alignment would be rare. If 3I Atlas happened to arrive with its spin axis aimed almost straight at the sun, that would be a statistically notable coincidence. If, in addition, a major active region happened to sit near one of the poles, the coincidence would deepen. If, beyond that, the inner coma happened to display a three-way symmetry suggestive of evenly spaced active regions, the sense of improbability would deepen again. This was how the argument developed, not through one sensational observation, but through the stacking of several smaller ones. The brightness variations added another layer. When astronomers monitored the object photometrically, they found that its brightness changed with a period of about 16 hours. That made sense for a rotating body, but the light curve was not as simple as that of a featureless, elongated object turning in sunlight. Instead, it suggested that variable jet activity was modulating the object's brightness. In other words, what we were seeing was not just the changing silhouette of a rotating nucleus, but the changing visibility of active outflows. That rotational heartbeat mattered because it tied the geometry to dynamics. It was one thing to see a static asymmetry in a coma. It was another to see a repeating pattern that implied a stable rotational structure over months of observation. If the object's dominant jet really did wobble within only a few degrees of the rotation axis, then the jet source must have been located very near a rotational pole. That was already a specific geometry. If that same pole also stayed roughly sunward through much of the object's passage, then the arrangement became even more specific. Researchers who were willing to contemplate technological possibilities pointed to that chain of alignments as suggestive. Researchers who preferred natural explanations argued that unusual objects can still be natural, especially when humanity has observed only a tiny number of confirmed interstellar visits. That caution is important. Our sample size is painfully small. Before 3I Atlas, only 2 confirmed interstellar objects had captured global attention, 1I Oumuamua and 2I Borisov. With such a tiny sample, it is difficult to know what counts as normal for interstellar bodies. Perhaps such objects are often strange because only strange ones are easy to detect. Perhaps the processes that eject them from their home systems favor unusual geometries, unusual chemistries, and unusual activity. Perhaps our own solar system has simply not prepared us for the range of possibilities that exists in the wider galaxy. That argument is entirely plausible, but 3I Atlas kept adding pressure to it. Chemistry was one reason why. Spectroscopic studies carried out with major ground-based telescopes found evidence for atomic nickel in the coma. Nickel itself was not the surprise. Nickel has been seen in cometary environments before. The surprise was what seemed to be missing alongside it: iron. In ordinary primitive material, nickel and iron are close companions. They are forged together in stellar processes and are usually found together in meteoritic and cometary matter. Detecting nickel without comparable evidence of iron therefore raised eyebrows. Whatever mechanism was releasing nickel into the coma appeared to be favoring that element in a way that standard cometary expectations did not predict. Several natural explanations were proposed. Perhaps nickel was bound in unusual organometallic compounds that were easier to break apart under sunlight. Perhaps the body formed in a chemically distinctive environment around another star. Perhaps its dust grains had experienced a unique thermal or irradiation history. All of those ideas are scientifically respectable. None is impossible, but the chemistry of 3I Atlas did not feel ordinary. Additional measurements complicated the picture further. The object also showed unusual relationships between nickel and cyanogen, and some studies suggested a depletion of familiar carbon chain species compared with ordinary comets. That did not mean the object was artificial. It meant only that its chemical fingerprint did not line up neatly with the fingerprints astronomers were used to reading. If 3I Atlas was natural, it was natural in a way we had not seen before. And then there was the radio silence. Whenever an object inspires public speculation about alien technology, one of the first questions becomes whether it is transmitting. Several major radio facilities turned their attention toward 3I Atlas, including instruments associated with the Breakthrough Listen effort. They searched across wide frequency ranges for narrowband or otherwise suspicious emissions that might indicate an artificial transmitter. They found nothing, That result was important because it constrained one popular fantasy, the idea of an active beacon announcing itself to Earth. If 3I Atlas carried such a beacon, it was not operating in the radio bands our searches covered, at least not in a way our instruments could detect. The object was silent. For many observers, that silence strongly favored the natural interpretation. A natural comet should be radio silent. A technological probe, they argued, ought to betray itself somehow. But even that argument was less decisive than it first appeared. A technological object would only be expected to transmit if it had a reason to do so, if it used communication methods we understood, and if it chose to reveal itself at all. A dormant artifact, an observational probe, or a silent device operating by unfamiliar means could easily produce no detectable radio signature. Silence, therefore, ruled out some technological scenarios, but not all. The radio results narrowed the field. They did not close the case. As the months passed, the public conversation around 3I Atlas split into two broad camps. One camp saw a weird but natural comet. The other saw an object whose weirdness was beginning to feel too organized to ignore. Most professional astronomers remained in the first camp, but even there, many admitted that the object was unusual enough to deserve close attention. The dispute was not really about whether it was strange. It was about how much strangeness nature is allowed before new categories must be considered. That is a more philosophical question than it first appears. Science does not work by defending normality, it works by confronting data. If a natural model explains the data, it survives. If it fails, it must be revised or replaced. The history of astronomy is full of cases where seemingly bizarre observations eventually found perfectly natural explanations. It is also full of cases where a stubborn anomaly led to a new understanding of the universe. The proper response is neither gullibility nor dismissal. It is disciplined curiosity. By that standard, 3I Atlas earned the attention it received. Its path through the solar system also played into the mystery. The object moved on a hyperbolic trajectory, confirming its interstellar origin. But some researchers became fascinated by how that path related to the planets. It passed close enough to several major bodies to be observed from multiple vantage points, almost as if the solar system had been arranged to showcase it. That, of course, may simply have been a selection effect. We noticed it because it was observable. Still, when multiple fortunate alignments pile up around a single object, people start to wonder. The most dramatic of these trajectory coincidences involved Jupiter. As 3I Atlas receded from the inner solar system, calculations suggested that in March 2026, it would pass at a distance astonishingly close to Jupiter's Hill radius, the approximate boundary within which Jupiter's gravity dominates over the Sun's for the purpose of retaining satellites. Some interpreted that near match as yet another coincidence in a long chain of them. Others treated it more cautiously, noting that with enough measured quantities, some numerical near-qualities are bound to look suggestive. That is true. Pattern recognition is both a strength and a weakness of the human mind. Still, the Hill radius encounter captured imaginations because it sounded purposeful. If one were trying to place something into the gravitational domain of Jupiter, skimming that boundary would be meaningful. Yet no evidence showed that 3I Atlas was attempting anything at all. There was no detection of deployed probes, no confirmed fragmentation event, no unmistakable maneuver. The object simply continued outward along its path. Once again, the pattern was provocative, but not conclusive. That phrase may be the most honest summary of the whole saga. Provocative, but not conclusive. It applies to the antitail. It applies to the symmetric jets. It applies to the chemistry. It applies to the trajectory coincidences. It applies to the photometric heartbeat. Each feature pointed toward a puzzle. None delivered a final answer. This is why 3I Atlas became so fascinating. It lived exactly in that uncomfortable zone between explanation and uncertainty. It was too odd to dismiss casually, yet not decisive enough to force a revolutionary conclusion. If it turns out to be natural, then 3I Atlas will still matter enormously. It will tell us that interstellar comets can adopt structures and behaviors more organized and more extreme than those we commonly see in native solar system bodies. It will force theorists to refine models of cometary activity, rotational dynamics, and chemical evolution under interstellar conditions. It will expand our idea of what nature alone can produce. If it turns out to be artificial, the consequences would be immeasurably larger. A technological origin would imply that intelligence had arisen elsewhere and developed the ability to send objects between the stars. Even a dead artifact would change humanity's view of itself forever. That is precisely why caution matters. Extraordinary possibilities create a powerful temptation to leap ahead of the data. But scientific credibility is preserved by resisting that temptation. The most responsible approach is to state clearly what is observed, what is inferred, and what remains unknown. What is observed? An interstellar object entered our solar system. It displayed comet-like activity. It developed a persistent sunward anti-tail. Its photometric behavior implied a roughly 16-hour rotational period. Processed Hubble images suggested a structured inner coma that may include 3 jets spaced about 120 degrees apart. Spectroscopy revealed unusual chemical features, including nickel without a comparably obvious iron signature. Radio searches found no evidence of artificial transmissions. What is inferred? The anti-tail likely reflects a highly directed outflow or a dust geometry more complex than ordinary cometary models predict. The rotational light curve likely involves active regions, not just shape. The inner coma probably contains stable directional structure tied to the rotation of the nucleus. The chemistry may indicate unusual mineralogy, unusual parent molecules, or formation in a distinct extra. What remains unknown? Almost everything that matters most. We do not know the exact shape of the nucleus. We do not know the detailed source regions of the jets. We do not know whether the apparent 120-degree symmetry is a deep physical property or an artifact of viewing geometry and image processing. We do not know how the anti-tail remains so focused. We do not know why the chemistry looks the way it does. We do not know whether all of these anomalies share one cause or several. And we certainly do not know whether the object is natural or technological. That uncertainty can be frustrating, but it is also what makes the case so scientifically rich. 3I Atlas arrived, disturbed our assumptions, and then continued outward. Humanity had only a narrow window to observe it while it was bright enough for intensive study. We used Hubble. We used giant ground-based telescopes. We used radio observatories. We measured, processed, modeled, and argued. And still, the object kept some of its essential mystery. That may ultimately be the most important lesson of all. Interstellar objects are not merely curiosities. They are messengers from environments we cannot visit. Each one carries information about another star system, another formation history, another set of physical conditions. Every time one passes through our solar system, we are being offered a sample of the wider galaxy. That sample may be humble, like an icy fragment knocked loose from a distant young system, or it may be something far stranger. The only honest position for now is that 3I Atlas remains unresolved. There are reasons to think it is a comet. There are reasons to think it is an extraordinary comet. There are reasons some researchers refuse to dismiss more radical possibilities. The object does not force a conclusion. It forces attention, and perhaps attention is exactly what it deserves. As 3I Atlas travels away from the Sun, its activity will gradually fade. The jets will weaken. The anti-tail will diminish. Its brightness will drop until only the largest telescopes can follow it, and eventually even they will lose the object against the black background of space. It will continue on its hyperbolic path toward the outer solar system and, in time, back into the interstellar darkness from which it came. We will not chase it down. Our spacecraft are too slow, and our opportunity came too late. Whatever close-range secrets the object holds are leaving with it. What remains behind are the data. The Hubble frames, the spectra, the light curves, the radio logs, the orbital solutions, the calculations, and the arguments. Those will be studied for years. New processing methods may reveal structures we have not yet noticed. Better models may show that what looked astonishing was actually natural after all. Or future interstellar visitors may provide the missing context, proving that 3I Atlas was either typical or even stranger than we realized. The coming era of sky surveys may help answer that. More sensitive observatories are expected to find many more interstellar objects in the years ahead. Once the sample grows beyond 2 or 3 rare cases, astronomers will finally be able to compare them in a meaningful way. Then we may learn whether 3I Atlas was a statistical fluke, an extreme member of a natural population, or an early hint that the galaxy contains categories of objects we have not yet learned to name. Until then, 3I Atlas remains what all great mysteries are at the beginning, not a solution, but a question sharpened by evidence. What was it? A comet with extraordinary luck and extraordinary physics. A natural object from another star system whose chemistry and geometry simply exceeded our expectations. A fragment of something more complex than a primitive icy body. Or, however unlikely it may seem, an artifact of design passing silently through our neighborhood. No one can yet. But the reason the story has endured is simple. 3I Atlas did not merely pass through the solar system. It forced us to confront the edge of our knowledge. It reminded us that the universe still contains objects capable of surprising even our best instruments and our most confident theories. And that may be the most important message hidden in its geometry. Not that we have already found the answer, but that the question is now impossible to ignore.